Welcome to Two Projects. In this video, we are going to explain about the project that is design of an early prediction model for Parkinson's disease using machine learning. So before getting into the execution, first let us understand what is the project about. So in your surroundings or in your home, there may be some elderly people. So they may shake hands slightly when holding a cup or that their movements have become slower than the usual. So this could be early sign of the Parkinson's disease, that is PD. It's a progressive disorder that affects the brain's ability to produce dopamine, which is a chemical essential for controlling the movement. So this PD, that is Parkinson's disease, doesn't just make simple tasks like walking or writing difficult. It also affects the coordination and muscle control, which causes stiffness and tremors. One of the earliest and most telling signs of this Parkinson's disease is a change in the speech. Many patients between 70 and 90% they experience difficulties such as weak or low voice, sudden bursts of speech, strained ones, or unusual long pauses while talking. So these speech changes often appear before more obvious physical symptoms, making them a key indicator for the early detection. Identifying Parkinson's disease at this stage is vital because timely diagnosis can allow interventions that improve quality of life and may even help to anticipate the other neurological conditions that share similar early symptoms. And coming to this machine learning techniques, they have become a valuable tools in detecting Parkinson's disease because they can analyze complex data patterns that are often difficult for humans to identify. For example, machine learning algorithms they can study subtle changes in the person's speech, handwriting, walking patterns, or medical images to detect early signs of PD. So these techniques have shown significant potential in making diagnosis faster and more accurate. However, there are still important challenges that limit their effectiveness. Many datasets used for training machine learning models are imbalanced, meaning they are far more samples of healthy individuals than the Parkinson's disease patients, which can be bias in the model. That is, which can lead to bias in the model. Additionally, datasets are often high dimensional, containing many features that may not all be useful, making it hard for models to focus on the most relevant information. So, selecting the right features and ensuring the models are interpretable for clinicians is also a critical concern. And here, overcoming these challenges is necessary to build ML models that are not only accurate but also reliable and practical for real world healthcare applications, enabling early detection and better treatment outcomes for the patients with Parkinson's disease. So, this project focuses on developing a model called XRFILR, that is explainable balanced recursive feature importance with the logistic regression. That is to predict the Parkinson's disease early using speech data. So goal of this project is to overcome common challenges in the machine learning based Parkinson's disease detection, such as datasets with imbalanced classes, large number of features, and models that are difficult to interpret. By addressing these issues, the system aims to provide reliable and clinically meaningful prediction. And here the workflow begins with the data pre-processing and data balancing. So the speech dataset is first cleaned and normalized to remove the noise or irrelevant information. And here to address the class imbalance, k-means synthetic minority oversampling technique, that is k-means mode, is applied generating synthetic samples of underrepresented classes. This ensures that the model learns effectively from both the Parkinson's and also the healthy samples. And dimensionality reduction technique, that is PCA, is used to reduce the number of features while preserving the most important information in the dataset. This helps to improve the computational efficiency and prevent the model from being overwhelmed by redundant or less informative features. And also feature selection techniques have been used, that is RFE with the logistic regression. So this identifies the most significant features that contribute to the Parkinson's disease prediction by selecting only the most relevant, and the model achieves high accuracy and also reduces overfitting. And in the next step, the selected features are used by the logistic regression and the other machine learning models, that is other machine learning classifiers, to predict the presence of Parkinson's disease. So logistic regression serves as the main classifier due to its efficiency and also the interpretability. And Shapley, that is Shapley additive explanations, SHAP, is employed to explain the contribution of each feature in the prediction. So this ensures that the model's decisions are transparent and also understandable, which is important for clinical applications. So these are the different techniques followed to detect the Parkinson's disease in the project. Furthermore, to improve the accuracy of this project, here we have employed voting classifier, which is an ensemble technique. It is employed as the extension model. So this voting classifier, it combines several models. So here we have combined multi-layer, perceptron, bagging, and logistic regression, leveraging the strengths of each algorithm to make more robust and reliable predictions for Parkinson's disease. And here we have also developed front-end using Flash framework for the user authentication. So this allows users to securely enter the speech data, displaying predictions results clearly, and provides a practical interface for testing the system. It makes the model more user-friendly and also accessible, enabling deployment for early Parkinson's disease detection. Now moving on to the implementation. So these are the steps followed in the flow of work to implement the project. Let us understand each step, step by step. So first, we have imported all the necessary libraries and packages from the Python to perform data processing, model building, evaluation, and front-end development. After that, we have examined the dataset to understand its structure, feature types, and any missing or inconsistent values. After that, we have pre-processed the data. So first, we have removed irrelevant or noisy data to ensure quality input, and then we normalize the features to a standard scale for better model performance. And then comes class balancing. So here, K-means smooth technique. It is applied to address the class imbalance by generating synthetic samples for the minority class, ensuring the model learns effectively from both the classes. After that, we have selected important features using this recursive feature elimination with the logistic regression. It is used to select the most important features, reducing dimensionality and also improving predictive accuracy. After that, we will be initializing all the machine learning models, and that initialized models will be trained on the dataset, that is the balanced dataset, to learn the patterns for predicting the Parkinson's disease. And all the trained models will be evaluated using the metrics accuracy, precision, recall, and FN score. And that metrics, that is the performance of each model, will be visually represented through graphs for comparison purpose. And the best model will be saved for the future use using this job lib. And coming to the part of front end, so here we have used a Flash-based web interface to develop the front end with the registration and login functionality using SQLite enabling secure user access. And in the front end, users will be able to provide the input that will be pre-processed at the back end. It will be fed to the train model, and then the train model will be giving us the prediction. So this is how we have implemented. Now moving on to the algorithms used. So these are the algorithms used in this project. To implement this project, we need two kinds of requirements, which are hardware and software. In hardware, we need operating system of Windows, processor of 5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Software are application of Anaconda, primary language of Python, front-end framework of Flask, back-end framework of Jupyter Notebook, database of SQLite 3, and front-end technologies are HTML, CSS, JavaScript, and Bootstrap 4. So this is the overview of the project. Now let's execute it. To execute, let's open the code folder of the project. These are the source code files which are important for this project. So here in this model folder, we have the algorithm information, which will be loaded into the project code during runtime of the application. And here in this folder, we have the data set. So let's open it. So this is the data set used in this project. It's being loaded. Just wait for a while. So here we got the data. So these are the different features using which we will be predicting the Parkinson's disease. Here, if you observe, we have n number of features. We have so many features. So that is why we have used PCA for dimensionality reduction and also recursive feature elimination for selecting the most important features. You can observe, right? There are so many features. So these are all the features that we have in this data set. And this is the output variable that we will be predicting. Close this. Get back. This is the static folder. So this folder consists of CSS, JavaScript, and Bootstrap files, which are important for the visual appeal. And this is the templates folder. This folder contains all the HTML pages used in this project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. And in this, we have test cases that we will be using in the front end, and this is the app.py file. This .py file contains the information related to frontend. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in HTML templates. And this is the notebook file, which is IPYNB. And this is the Jupyter notebook file. It contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, which makes it a popular choice for the data science. And this is the signup.db file. This file is the database file which is used to store the user information. So this is all about the code folder. Now let's execute. So copy the path of the code folder from the address bar of the file explorer. I have copied it. Now open Anaconda prompt. So it is open. Now give the command cd, give the space, paste the copied path. Now click on enter. Here if you observe, current directory is changed to the code folder's path. Now compile app.py file. So give the command python space app.py and now click on enter. This command will execute Python script and perform a runtime check for any syntax issues, that is the syntax errors or logical issues. And after running the app.py file, Flask framework will host the application locally at the default address, which is the local host and the port. So this is the local host and this 5000 is the port. Now copy this local link provided by the Flask framework and paste it in any web browser. I'm copying it. Now I prefer Chrome, so I will be pasting the link in that. So paste the link here, click on enter. So here, this is the web page of the project, which is developed using Flask framework. So we need to sign up first. Click on sign up and enter all the registration details if you have not created the account. I have already created, so I will directly sign in. Click on sign in. Give your username and the password. Now click on sign in. We have signed in successfully and redirected to prediction page of the project. So here you can see prediction button, right? Click on that. So here you can see features, right? So these are the features that are to be given as input. So let's understand them. So first we have is mean MFCC feature. So the first one we have is the mean MFCC. It is the average value of the first MFCC coefficient representing overall spectral characters of the voice. And then we have standard MFCC second coef. It is a standard deviation of the second MFCC coefficient. And here we have standard ninth delta. It is the standard deviation of the ninth MFCC delta coefficient. And here we have standard delta log energy. It's a variability in the rate of the change of speech energy, reflecting intensity fluctuations. And then we have this one is the standard sixth delta. So this is the variation in the sixth delta coefficient. And here we have standard seventh delta. So it is a variation in the seventh delta coefficient showing temporal dynamics in the speech patterns. And then here we have det entropy log 1 coef. It is the logarithmic entropy of the first coefficient measuring randomness or the disorder in the speech signal. And then we have app TKEO standard 2 coefficient. It is the standard deviation of the Tiger-Kaiser energy operator for the second coefficient capturing energy variations in the speech. And then we have TQWT, that is tunable Q factor valved transform features. So this TQWT energy DEC25, it is the energy in the 25th valved decomposition level representing signal intensity in the specific frequency bands. And then we have TQWT entropy Shannon deck 3. Here we have 17, 27, 35. So here, these are the logarithmic entropy at various TQWT levels, another measure of signal complexity. And here we have TQWT Shannon entropy 17. It is the average Teaser-Kaiser energy at decomposition 17, reflecting average energy in the frequency band. And here we have TQWT 12. So here we have TQT, WT 12. So 12, 19, and 22. So these are the standard deviation of teaser, that is Tiger Kaiser energy at the decomposition 12 and 19, capturing variability of the energy. After that, we have TQWT standard value 2. So this is the standard deviation at the decomposition 2, showing variability in the signal at that level. And here we have TQWT min value DEC 17, that is the minimum value of the valved coefficients at the decomposition 17. It indicates the lowest signal intensity. And here we have TQWT max value DEC 5 and DEC 20. It is a maximum valved coefficient values at the decompositions 5 and 20, capturing peak energy. And here we have TQW Curtis's value DEC 17, 31, and 33. So these are the Curtises, that is the peakness of valved coefficients at the decompositions 17, 31, and 33, indicating the extreme deviations of the spikes in the signal. So this is all about the coefficients, sorry, the features. Now let's execute. So let's open the sample file. So this is the sample file. So these are the input features that we're supposed to give. So here, the first one, let's try with the first case where mean MFCC is 8.4781 and the next one is 0.78036. In this way, we need to enter all the inputs. So here I have entered all the features. So here you can observe I have entered all the features. Now let's click on submit now. And this information, it will be pre-processed at the backend. It will be fed with the train model and then train model will be giving us the prediction. So here we got the prediction that the analysis suggests the presence of Parkinson's disease. That means the patient is having Parkinson's disease. Now let's check with the other values. So now let's check with this case. So here I have entered all the parameters. Now click on submit now. And here we got the prediction that the analysis suggests the presence of Parkinson's disease. Now let's check with the other class. So let's apply filter to the class label. Now let's check with the class 0. So now let's check with the first one, the first parameter. Now click on predict again. So here we're supposed to enter that is 6.6578. In this way, let's enter all the parameters. So I have entered all the parameters of class 0. Now let's check the prediction. Now click on submit now. So here we got the prediction that the analysis suggests that normal data, there is no Parkinson's disease. Now let's check with the last case. So now let's check with this one. So let's enter them. Here we have 4.1875. Similarly, let's enter all the other parameters. So here I have entered all the parameters. Now let's click on submit now. And here we got the prediction that normal data. There is no Parkinson's disease for the patient. Now let's check with the graphs. Click on about. So here we have the graphs. The first graph, which we have is the sample outcome graph in the pie chart. So here this orange line represents Parkinson's disease and this blue color represents 24.1. And here, this is the balanced sample outcomes. Here, if you observe, Parkinson's disease samples are more than the healthy ones. So here, we have used balancing technique and balance the data. So here you can see both the classes are equally distributed. And this is the confusion matrix. This is the heat map, which shows the class distribution. So that is the relation between variables, correlation between the variables. And here we have variance of the selected features. So this is the variance of the selected features. And this is the variance ratio. And here we have accuracy score comparison graph. So here on x-axis, we have all the algorithm names and on y-axis, we have accuracy. Similarly, we have precision, recall, FN score, ROC, AUC. And here we have sharp value. So these are the feature important graphs. So this is all about the graphs. Now click on log out. In this page, just by giving required parameters to the application will be predicting whether the person has Parkinson's disease or not. So this is all about the project.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.